Hey there, and welcome back to Deep Space Intelligence. I'm Liam, and if you're new here, this is the place where we take the biggest, strangest, most unsettling questions in science and space exploration, and we follow them wherever they lead. No shortcuts, no easy answers, just honest investigation into the universe we all live in. Today's question is one of those that sounds almost too simple when you first hear it, but the more you turn it over in your mind, the more it starts to feel like a cold wind blowing through an empty room. Today we're asking why. Why haven't we found anyone else out there? Stand outside on a clear night, look up, let your eyes adjust to the dark. What you're seeing, even with the naked eye, is barely the beginning. Our Milky Way alone contains somewhere in the range of 400 billion stars. Around those stars, astronomers now estimate there orbit at least 1 trillion planets. Maybe more, maybe far more. Expand that picture outward to the observable universe, and the numbers stop feeling like mathematics and start feeling like something your brain was never designed to process. There are approximately 2 trillion galaxies in the space we can observe, each one a vast collection of stars, each star a potential sun to worlds we have never seen. When astronomers sat down and tried to calculate how many planets likely exist in the observable universe, they arrived at a number so large it becomes almost meaningless to pronounce roughly 100 sextillion. That is one followed by 23 zeros. For context, researchers at the University of Hawaii estimated that there are about 7 quintillion 500 quadrillion grains of sand on all of Earth's beaches and deserts combined. The number of planets in the universe exceeds even that colossal figure by a factor of 10,000. So by the sheer force of mathematics, by the logic of probability, by any rational calculation, life should be out there. It should be everywhere. We should have heard something by now. Some faint signal cutting through the static of cosmic background radiation, some unmistakable sign of chemistry being bent toward purpose on some distant world. And yet the universe, for all its incomprehensible scale and age, remains profoundly, stubbornly, almost accusingly silent. This is what keeps astronomers awake at night. Not the search itself, because the search is exciting and full of momentum, but the silence. The extraordinary, decade-spanning, instrument-straining silence. Before we go deeper, I want to say something directly. Here at Deep Space Intelligence, we work hard to present the science as accurately and honestly as we can, drawing on peer-reviewed research, statements from scientists, and data from space missions. But this is a topic where the science itself is genuinely unsettled, where the world's best minds genuinely disagree, and where the data we have is still frustratingly incomplete. I'd always encourage you to dig into the primary sources yourself, to read the actual papers, to listen to the astronomers and astrobiologists, and to form your own view. The goal here is never to tell you what to think, it's to think alongside you, now. Let's start at the beginning of this story, which begins, appropriately enough, at a lunch table. It was a summer day in 1950 in New Mexico. The setting was the Fuller Lodge at Los Alamos National Laboratory, the same facility that had, only a few years earlier, been the secret heart of the Manhattan Project. The Cold War was underway. The Soviet Union had just detonated its first atomic bomb, and a tight cluster of the world's most brilliant physicists had gathered in the desert to work on what came next. On this particular afternoon, 4 of them were walking to lunch together: Enrico Fermi, Edward Teller, Emil Konopinski, and Herbert York. Fermi was, by any reasonable measure, one of the finest scientific minds of the 20th century. He had won the Nobel Prize in Physics in 1938. He had led the team that built the world's first nuclear reactor in a converted squash court beneath the University of Chicago. He was legendary among his colleagues for his ability to perform rapid, startling calculations in his head, reducing enormous unknowns to intuitive estimates with unsettling accuracy. And walking to lunch that day, he had been half listening to a conversation about flying saucers, a topic that had recently captured the American popular imagination. The conversation at the table eventually drifted to other things, the way lunch conversations do. And then, according to Edward Teller's recollection, right in the middle of discussing something else entirely, Fermi blurted out a question. He asked it casually, almost like an afterthought. He said, in words that have been paraphrased and refined over decades, but whose meaning remains perfectly clear, "Where is everybody?" Teller later wrote that the result of the question was general laughter, not because it was absurd, but because everyone at the table understood instantly, without any explanation exactly what Fermi was asking. He was asking about alien civilizations. He was noting, with the quiet confidence of a man who had done the calculation in his head in about 30 seconds, that the universe was old enough and large enough and full enough of potential suns and worlds that some other civilization somewhere should have had the time to develop technology, to expand outward, to fill the galaxy, to reach us, or at least to make themselves known, and they hadn't. And that was very, very strange. Herbert York later recalled that Fermi followed up his question with a rapid series of calculations at the table, estimating the probability of Earth-like planets, the probability that life would arise on such a planet, the likelihood of intelligence emerging from that life, and the expected lifespan of a technological civilization. He ran through the numbers and concluded, with characteristic directness, that by all reasonable estimates we should have been visited long ago, and not once, but many times over. Fermi died of cancer in 1954, only 4 years after that lunch, before any of this became a formal field of study. The conversation remained a kind of oral legend within the Los Alamos community, one of those stories passed between physicists at conferences and over coffee. In 1984, a physicist named Eric Jones tracked down the 3 surviving participants and wrote up their accounts. That document forms the historical foundation of what we now call the Fermi Paradox. What makes Fermi's question so enduring is not just that it was clever, it's that 75 years later, with radio telescopes the size of football fields, space observatories of breathtaking precision, and computing power Fermi could not have imagined, the answer remains exactly as it was when he asked. We still don't know, and the silence, if anything, has grown louder. Let's talk about scale for a moment, because I think it's the only honest place to start. When we say the universe is large, we tend to nod and move on, the way we nod at a price tag we don't fully believe. But the reality of cosmic scale is something worth sitting with, because it's the foundation of everything that follows. The observable universe, meaning the portion of space from which light has had time to reach us since the Big Bang, has a diameter of roughly 93 billion light-years. A light-year is the distance light travels in a single year, moving at 300,000 kilometers per second. The nearest star to our own Sun, Proxima Centauri, is about 4.2 light-years away. If you built a scale model in which that distance was 1 centimeter, the diameter of the observable universe would be over 2 million kilometers. The actual universe, the part we cannot see because light from it hasn't reached us yet, may be vastly larger still. Within this observable universe, those roughly 2 trillion galaxies are distributed across filaments and walls of structure, separated by vast cosmic voids. Each galaxy is not a single point, but a system containing billions or hundreds of billions of stars, each of those stars a gravitational anchor around which planets potentially orbit. Our own Milky Way, a fairly average barred spiral galaxy, contains around 400 billion stars. That means that even within our own galaxy, the number of potential worlds is staggering. In 2013, astronomers using data from NASA's Kepler Space Telescope made a finding that shifted the entire field. They determined that, on average, every star in our galaxy hosts at least one planet. That single result transformed an ancient philosophical question into a statistical near-certainty. There are more planets in the Milky Way than there are stars. The estimates range from 1 trillion to perhaps 10 trillion orbiting planets in our galaxy alone, and that number doesn't even include the so-called rogue planets, worlds flung free from their home solar systems by gravitational chaos, wandering the dark between the stars without any sun at all. Some estimates suggest rogue planets could outnumber orbiting ones by 10 to 1. Based on these numbers, astronomers have estimated that, within our galaxy, there may be 60 billion planets sitting in what scientists call the habitable zone of their stars. That is the range of distances from a star at which liquid water could theoretically exist on a planet's surface. Not too hot, not too cold, the celestial sweet spot that, as far as we know, is a prerequisite for life as we understand it. And life as we understand it is itself a phrase worth pausing on. Because everything we know about life, its chemistry, its requirements, its origins, is based on a sample size of exactly 1, Earth. We have one example, and from that one example, we have extrapolated enormously. We've decided that liquid water is essential. We've decided that carbon-based chemistry is the foundation. We've decided that a stable energy source and a suitable atmosphere are necessary. these assumptions are reasonable. They are grounded in our best understanding of biochemistry and planetary science. But they are still assumptions built on a single data point. The history of science is full of moments when a single data point turned out to be genuinely representative of a larger pattern. It is also full of moments when it wasn't. We should hold both possibilities in mind. So let's talk about where we actually stand in the search for that second data point. In 1960, a young radio astronomer named Frank Drake pointed an 85-foot telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia, at two nearby stars, Tau Ceti and Epsilon Eridani. He tuned the telescope to a frequency of 1,420 MHz, the frequency at which hydrogen atoms naturally emit radiation. Drake's reasoning was elegant. Hydrogen is the most abundant element in the universe. Any civilization advanced enough to use radio technology would almost certainly know that frequency. It was, in effect, a cosmic common denominator. His project was called Project Ozma. For 4 months, Drake listened. He heard nothing that could not be explained by natural sources. But the experiment was not a failure. It was a beginning. It crystallized the idea that we could, in principle, detect evidence of technological life across stellar distances, and it led directly to a meeting in 1961 that changed how scientists thought about the problem. At that meeting, held at Green Bank and attended by luminaries including Carl Sagan, Drake introduced what became known as the Drake equation. It was not, strictly speaking, an equation in the sense that it could be solved. It was more of a structured way of decomposing the problem, a framework for organizing ignorance. The equation asked, how many stars form in our galaxy per year that are suitable for the development of life? Of those stars, how many have planetary systems? Of those planetary systems, how many have planets in habitable zones? Of those planets, on how many does life actually arise? Of those, on how many does intelligent life evolve? Of those, on how many does that intelligence develop technology capable of communicating across space? And of those, how many are still transmitting at this particular moment in cosmic time? Every one of those terms, when Drake and his colleagues first sat down in 1961, was essentially unknown. They made guesses, educated guesses, the best guesses available, and arrived at an estimate suggesting that new communicating civilizations should be appearing in our galaxy, roughly once a year. Multiply that by the average lifespan of a civilization, and you get the number of civilizations that might exist at any given moment. The problem, the beautiful and devastating problem, is that the last term in the Drake equation, the average lifespan of a technological civilization, is entirely unknown. And it might, as some researchers have bleakly suggested, be very short indeed. In the 6 decades since Drake introduced his framework, some of the early terms have become measurable. We now know that nearly every star has planets. We have a reasonable estimate of how many of those planets sit in habitable zones. We know that the chemistry needed for life, the organic molecules, the amino acids, the precursors of RNA and proteins, form spontaneously in interstellar space, in comets, in meteorites, in the primitive atmospheres of young planets. We know all of this, and the silence remains. The SETI program, the search for extraterrestrial intelligence, has been listening across dozens of frequencies for decades. Enormous radio arrays have swept the sky. No confirmed artificial signal from beyond our solar system has ever been detected. Not one. There have been candidates over the years, the most famous being the signal detected by astronomer Jerry Eman in 1977 using the Big Ear telescope at Ohio State University, a signal so anomalous that Eman circled it on the printout and wrote a single word in the margin: wow. That signal, known ever since as the wow signal, has never been explained and has never repeated. Some researchers have proposed it was a natural source, others have speculated otherwise, we still don't know. But no confirmed signal. Across all the frequencies we've monitored, across all the directions we've pointed our instruments, across all the years of listening, nothing has come back. This is not necessarily evidence that no one is out there. It might mean they don't use radio waves. It might mean the signals are too faint or too brief for our instruments to catch. It might mean they're transmitting in a mode we haven't thought to look for yet. It might mean any number of things. But it is a fact that demands explanation, and scientists have spent decades trying to construct one. The explanations, broadly, fall into 2 categories. Either we haven't found life because it isn't there, or we haven't found it because of limitations we don't yet understand, limitations of distance, of time, of technology, or of our own assumptions about what life and intelligence look like. Let's explore the first category, because it leads us into some of the most fascinating and sobering science of the past century. One of the most influential ideas about why the universe might be empty of detectable intelligent life is called the rare earth hypothesis. It was developed by paleontologist Peter Ward and astronomer Donald Brownlee, both of the University of Washington, and published in their 2000 book of the same name. The core argument of the rare earth hypothesis is that while microbial life might be common in the universe, complex multicellular life of the kind that eventually produces intelligence is extraordinarily rare, not because the universe is hostile to it, but because the precise conditions required for it to emerge are so specific, so narrowly defined by so many independent factors that must all align simultaneously, that the probability of it happening twice in any given galaxy is vanishingly small. Ward and Brownlee were not being mystical. They were being rigorous. They worked through a list of factors that they argued were necessary for complex life to evolve on Earth, and they asked how likely each was to be replicated elsewhere. Start with the galaxy itself. Our solar system sits in what astronomers call the galactic habitable zone, a ring-shaped region in the Milky Way roughly 7 to 9 kiloparsecs from the galactic centre. Too close to the centre, and the radiation from dense stellar clusters and the activity near the supermassive black hole at the galaxy's core would sterilize any developing biosphere. Too far from the centre, and the interstellar medium lacks the heavy elements produced by generations of stellar evolution: the carbon, oxygen, nitrogen, phosphorus, iron, the very atoms from which planets and living things are assembled. Our position in the galaxy, roughly midway out on one of the spiral arms, turns out to be something of a cosmic Goldilocks condition, and according to astronomer Charles Lineweaver, perhaps only 10% of stars in the Milky Way fall within a comparable zone. Then consider our star. The Sun is a G-type main sequence star, a relatively stable, middle-aged, medium brightness star that has been burning consistently for about 4.6 billion years, and will continue to do so for roughly 5 billion more. Most stars in the galaxy are M-class red dwarfs, smaller, cooler, and far longer lived. For years, red dwarfs were considered promising hosts for habitable worlds because they are so abundant, making up about 80% of all stars in the Milky Way. But ongoing research has complicated that picture significantly. Red dwarf stars are prone to violent stellar flares that blast their nearby planets with radiation. Because a habitable zone planet around a red dwarf must orbit very close to its star, it is likely to become tidally locked, one face permanently turned toward the star in unbroken scorching daylight, the other in permanent freezing night. While scientists debate whether such worlds could still harbour life in the twilight zones between their permanent day and night sides, the conditions are challenging in ways that our own world never had to overcome. Our star, then, with its relative stability, its position in the galaxy, and its particular luminosity, may itself be a somewhat rare gift. Move from the star to the planet. Earth occupies the habitable zone of the Sun, the range of orbital distances at which water can exist as a liquid on a planetary surface under the right atmospheric conditions. But habitable zone alone does not a living world make. Earth also has plate tectonics, the geological process by which the planet's crust is divided into moving sections that collide, slide beneath one another, and resurface. This process, unique among the rocky planets of our solar system, does something crucial. It acts as a planetary thermostat, cycling carbon dioxide between the atmosphere and the crust over millions of years, regulating the greenhouse effect, preventing the kind of runaway warming that consumed Venus and the atmospheric collapse that likely contributed to the freezing of Mars. Earth also has a large moon. Our moon is the largest moon relative to its host planet in the solar system, excluding dwarf planet systems. The presence of this unusually massive companion stabilizes the tilt of Earth's rotational axis, keeping it within a relatively narrow range over geological time. If Earth's axial tilt were to wander dramatically, as it would without the Moon's gravitational steadying influence, the climate variations would be far more extreme, seasons would become violent and unpredictable at geological timescales, and the long periods of stable conditions that may have been necessary for complex life to evolve could have been disrupted or prevented entirely. And then there is Jupiter, the solar system's largest planet sitting beyond the asteroid belt in a nearly circular orbit, acts as a gravitational shield. Its massive gravity deflects or captures many of the comets and asteroids that would otherwise bombard the inner solar system far more frequently. While some comet impacts early in Earth's history may have delivered water to the planet, reducing the frequency of large impacts over the last several 100 million years has likely been important for allowing complex life to persist and diversify without constant extinction-level disruptions. Consider what we have described so far: a position in the galactic habitable zone, a stable G-type star at the right distance, a rocky planet with liquid water, plate tectonics, and a carbon cycle, a large stabilizing moon, and a distant giant planet acting as a gravitational bodyguard. These conditions are each individually somewhat improbable. Together, the joint probability of all of them occurring on the same world starts to look very small indeed. Ward and Brownlee went further, adding a magnetic field strong enough to deflect the solar wind that would otherwise strip the atmosphere, an appropriate planetary mass to retain that atmosphere without growing so large as to become a gas giant, and several other factors. Their argument, stated plainly, is that Earth is not typical. Earth is a rare winner of a very long cosmic lottery. The rare Earth hypothesis has not gone unchallenged. Some researchers argue that Ward and Brownlee have been too conservative, that life might find ways to thrive under conditions far outside those present on Earth, that the very definition of habitable is a moving target as our understanding of extremophils continues to expand. Extremophils are organisms that thrive in conditions previously thought incompatible with life. We've found microbes living in the cooling water of nuclear reactors, in highly acidic volcanic springs, in the perpetual darkness of deep-sea hydrothermal vents, in the ice of Antarctic lakes sealed from sunlight for millions of years. Life on Earth, once you start looking, turns out to be almost perversely adaptable. But even granting this flexibility, the rare Earth hypothesis raises a point that cannot simply be argued away. The specific path from the first self-replicating molecule to a technological civilization capable of building radio telescopes involves an enormous number of contingent steps, each of which had to proceed in a particular way. Every mass extinction that cleared the ecological stage for something new to evolve, every geological or climatic event that drove adaptation. The emergence of eukaryotic cells with nuclei and the capacity for sexual reproduction, an innovation that took roughly 2 billion years to develop after the first microbial life appeared on Earth. The Cambrian explosion, during which the basic body plans of most animal life appeared over a geologically brief period around 540 million years ago. The evolution of vertebrates, of tetrapods, of mammals, of primates, of the particular branch of great apes that developed language and abstract reasoning. Every one of these steps had alternatives. Every one of these steps could have gone a different way. Looking back at the history of life on Earth, it looks less like a straight road toward intelligence, and more like a winding path through an enormous maze, one that happened, by some combination of chance, environmental pressure, and biological invention, to lead to us. How many other paths through other mazes lead to intelligence? We genuinely do not know. This brings us to a related and deeply troubling concept, the Great Filter. The idea was formally articulated in 1998 by economist and philosopher Robin Hanson in an essay titled, in perfectly unambiguous terms, The Great Filter, Are We Almost Past It? Hanson's argument begins from the same place Fermi's did. Given the size and age of the universe, we should expect to see evidence of advanced civilization somewhere. We don't. Therefore, something is preventing them from appearing or persisting. That something is the Great Filter. The Great Filter, in Hanson's formulation, is a stage or set of stages in the development of life that is so extraordinarily improbable, or so catastrophically lethal, that virtually no species ever passes through it to become a galaxy-colonizing civilization. The filter could be behind us, meaning that one of the steps we have already taken in our evolutionary and civilizational history was the nearly impossible one. Or the filter could be ahead of us, meaning that something catastrophic awaits technological civilizations, something that destroys them before they can spread, something we have not yet encountered. The distinction between these two possibilities is, according to Hanson and later Nick Bostrom of Oxford University's Future of Humanity Institute, not merely academic, it is existential. If the Great Filter is behind us, that is cause for quiet optimism. It means that the impossibly difficult step, whatever it was, abiogenesis perhaps, or the emergence of eukaryotic cells, or the evolution of complex nervous systems, is something we have already cleared. We may be genuinely rare, but we are alive, and we have the future in front of us. But if the filter is ahead of us, then every civilization that reaches our level of technological development is, in some sense, approaching a cliff edge it cannot see. Something destroys them all, reliably and completely, before they can colonize the stars. Nuclear war, climate collapse, the development of artificial intelligence they cannot control, some as yet unimagined catastrophe inherent to the nature of technological civilization itself. Under this scenario, the universe would be filled with the ruins of civilizations that rose and fell quietly, too briefly, and too locally to leave any trace visible across interstellar distances. Bostrom took this logic to its darkest possible conclusion. He wrote that the discovery of life on Mars, even simple microbial life, would be the worst news humanity had ever received. Not because Martian microbes would threaten us, but because their existence would eliminate several of the candidate great filters that might lie behind us. If life arose independently on Mars, it means abiogenesis, the emergence of life from non-living chemistry, is not the nearly impossible step we hoped it might be. And if the filter is not in abiogenesis, it must be somewhere further along the road, perhaps in the very stage of development we now occupy. The search for life on Mars, then, and in the oceans of Europa and Enceladus, and in the atmospheres of exoplanets, is not only the grandest scientific quest in human history, it is also, potentially, the delivery of a verdict about our own future. A finding of nothing, of absolute sterility everywhere else we look, would be, in a strange way, the best news possible. It would suggest that we are the rare exception, that the filter is behind us, and that the cosmos is waiting to be explored. Understanding the great filter requires understanding something about the origins of life itself, because one of the most natural candidates for a great filter behind us is the extraordinary improbability of life beginning in the first place. In 1953, a graduate student named Stanley Miller, working in the laboratory of Harold Urey at the University of Chicago, set up a glass apparatus containing water, methane, ammonia, and hydrogen, substances thought to represent the chemistry of the early Earth. He sealed the system, applied heat to simulate the ocean, and electrical sparks to simulate lightning, and ran the experiment for a week. When he analyzed the resulting mixture, he found amino acids, the fundamental building blocks of proteins. He had created organic molecules from inorganic chemistry. The experiment became one of the most famous in the history of science. Miller's results were remarkable. They demonstrated that the raw materials of life could form spontaneously under plausibly natural conditions. In the decades since, chemists have found that amino acids form readily in the cold of interstellar space, attached to dust grains, carried inside meteorites, delivered to young planets by cometary bombardment. The Murchison meteorite that fell in Australia in 1969 contained more than 90 different amino acids, many of them not found in any biological process on Earth. Organic chemistry, it turns out, is not rare. The universe manufactures the alphabet of life in enormous quantities. But there is an enormous distance between the alphabet and the sentence. Having amino acids is very different from having proteins. Having proteins is very different from having a self-replicating molecule capable of passing information between generations. Having a self-replicating molecule is very different from having a cell with a membrane, an energy system, and the full biochemical machinery of life. And having a simple single-celled organism is a very different thing from having eukaryotic cells with nuclei, which is in turn utterly unlike having multicellular animals. The most widely accepted scientific framework for explaining the origin of life is something called the RNA world hypothesis. It proposes that before the current system of DNA storing information and proteins carrying out biochemical functions, there was an earlier era in which RNA molecules served both roles simultaneously. RNA is similar to DNA but typically single-stranded, and certain RNA molecules known as ribozymes can act as their own enzymes, folding into shapes that catalyze chemical reactions. The RNA world hypothesis suggests that the first self-replicating molecules were RNA-based, and that DNA and proteins took over later as the system evolved greater stability and efficiency. The RNA world is currently the leading scientific hypothesis for the origin of life, supported by a substantial and growing body of evidence. Researchers have shown that RNA nucleotides can form under prebiotic conditions, that short RNA sequences can self-replicate in laboratory environments, and that the ribosome, the molecular machine inside every living cell that reads genetic instructions to assemble proteins, is itself primarily made of RNA, and is thought to be a relic of the ancient RNA world. But even proponents of the RNA world hypothesis acknowledge that critical steps remain unexplained. How did the first RNA molecules long enough to self-replicate actually form? How did they acquire a membrane to separate their chemistry from the surrounding environment? How did the transition from an RNA-based system to the more complex and stable DNA protein system occur? These are not rhetorical questions. They are active research problems at the frontiers of chemistry and biology, and they remain genuinely unsolved. What this means is that we do not fully understand how life began on Earth, on the one planet we know for certain produced it. We know it happened relatively quickly in geological terms, within the first few 100 million years of Earth's existence, which was itself only formed about 4.5 billion years ago. We know it happened in water. We know it happened in the presence of energy and organic chemistry. Beyond that, the details are contested, the mechanisms are hypothetical, and the probability of the whole process remains, to put it plainly, unknown. If the probability of a biogenesis occurring on any given habitable planet is very low, then the great filter may lie at this very first step. Life, on this view, is an extraordinarily improbable accident that happened here, and perhaps rarely if ever happened elsewhere. The universe would be full of sterile worlds bathed in organic chemistry, but devoid of anything that uses that chemistry to grow and replicate, and eventually, possibly, to wonder about the stars. If, on the other hand, a biogenesis is not particularly improbable, if life emerges readily wherever chemistry and energy and water combine for long enough, then the great filter must lie somewhere further along the path, and the longer the path gets before the filter appears, the more disturbing its nature becomes. Because the further along we are before something destroys us, the more advanced whatever is doing the destroying must be. Let's talk about what we know of the universe's capacity for harbouring life beyond the first step. In the past 3 decades, the discovery of exoplanets, planets, orbiting other stars, has transformed astrobiology from a largely theoretical discipline into an observational one. It began in 1992 when astronomers Alexander Wolszczan and Dale Frail detected 2 planets orbiting a pulsar, the remnant of a supernova, using the Doppler wobble of the pulsar's radio pulses. 3 years later, in 1995, Michel Mayor and Didier Queloz detected 51 Pegasi b, the first confirmed exoplanet orbiting a normal Sun-like star, a gas giant so close to its star that its year lasted only 4 Earth days. Mayor and Queloz received the Nobel Prize in Physics in 2019 for this discovery, recognition that the scientific community considered it among the most consequential findings in the history of astronomy. The floodgates opened. The Kepler Space Telescope, launched in 2009 and retired in 2018, stared at a single patch of sky containing more than 100,000 stars and monitored them for the tiny dimming that occurs when a planet passes in front of its host star, a technique called the transit method. Kepler found over 2,700 confirmed exoplanets. Its data, still being analysed, has revealed that the universe is overflowing with worlds. Rocky planets, gas giants, ocean worlds covered entirely in deep water, planets far hotter than Mercury orbiting closer to their stars than any planet in our solar system, and planets so cold and far from their stars that any surface liquid would have frozen billions of years ago. Among the most important findings of the Kepler mission was a category of planets sometimes called super-Earths, or mini-Neptunes, worlds between 1 and 4 times the size of Earth. These planets appear to be the most common type in the galaxy, yet our own solar system contains none of them. Their frequency means they likely play some role in the distribution of potentially habitable environments across the cosmos, but their true nature, whether they are rocky and potentially habitable or ocean worlds shrouded in thick hydrogen atmospheres, is still being sorted out. The Transiting Exoplanet Survey satellite, known as TESS, was launched in 2018 and has continued Kepler's work, surveying not a single patch of sky, but almost the entire sky, looking for planets around the nearest and brightest stars. As of early 2025, TESS has contributed thousands of additional confirmed exoplanet candidates, including several rocky worlds in the habitable zones of nearby stars. The nearest potentially habitable world beyond our solar system may be Proxima Centauri b, a rocky planet orbiting in the habitable zone of the red dwarf Proxima Centauri, just 4.2 light-years away. Whether it actually harbours life is entirely unknown. Even if it does, the closest it could possibly communicate with us is a message that would take 4.2 years travelling at the speed of light to cross the void between us, and another 4.2 years for any reply to return. And then there is the James Webb Space Telescope, the most powerful space observatory ever built, launched on Christmas Day 2021, with a primary mirror 6.5 metres in diameter, cooled to temperatures just 7 degrees above absolute zero, and capable of detecting the chemical composition of exoplanet atmospheres through a technique called transmission spectroscopy. When a planet passes in front of its star, a tiny fraction of the starlight filters through the planet's atmosphere on its way to our telescopes. Different molecules absorb different wavelengths of light, leaving characteristic fingerprints in the spectrum. By reading those fingerprints, Webb can tell us what gases are present in atmospheres across interstellar distances. Webb has already made extraordinary strides. It has detected carbon dioxide, methane and water vapour in the atmospheres of planets ranging from hot gas giants to sub-Neptunes. It has found evidence of silicate clouds on distant worlds. In 2025, a team led by the University of Cambridge reported what may be the most consequential finding yet: tentative evidence for the presence of dimethyl sulfide and related sulfur compounds in the atmosphere of K2-18b, a sub-Neptune planet orbiting in the habitable zone of a red dwarf star about 120 light-years away. Dimethyl sulfide is produced on Earth almost exclusively by marine microorganisms, specifically by the metabolism of phytoplankton. On our planet, it is considered a biosignature gas, a molecule whose presence strongly suggests biology. The Cambridge team was careful to note that their detection was suggestive, not definitive, and that the signal required confirmation. Scientists at institutions including the Jet Propulsion Laboratory and MIT have pointed out that the 3 criteria for a genuine biosignature detection, a strong signal, an unambiguous molecular identification, and consistency with the planet's known environment, are not yet fully met by the K2-18b data. The claim is alive and actively being investigated, but it has not been confirmed. But the fact that we are even capable of having this conversation, the fact that a telescope orbiting the Sun 1.5 million kilometres from Earth can detect the potential chemical breath of possible life on a world over 1 trillion kilometres away, is staggering. We are, for the first time in human history, equipped with instruments powerful enough to look for life beyond our solar system. Not with certainty, not with perfection, but with genuine scientific reach. This is why the silence is becoming harder to dismiss. We are no longer simply staring at the stars and wondering. We are building instruments capable of answering the question, and the question is resisting even those instruments. One of the things I want to emphasize whenever we discuss topics like this is the difference between what the science actually says and what we might want it to say. The question of whether we are alone is one of the most emotionally loaded questions in all of human experience. It touches something deep in our sense of identity, our cosmology, our intuitions about meaning and significance. It is very easy, in discussing this topic, to unconsciously shade the evidence toward one desired conclusion or another, toward the comforting warmth of cosmic company, or toward the electrifying vertigo of absolute solitude. I'd encourage you to check the actual papers, to look at what the scientists themselves are claiming, and to be skeptical of any account, including this one, that seems to have a preferred answer built into the framing. Science at its best is comfortable with uncertainty, and so should we be. Now, with that said, let's return to the catalogue of possible explanations for the Great Silence, because some of the most interesting ones involve not the rarity of life itself, but the nature of intelligence and technological civilization. Even if life is common, even if it arises readily on worlds with the right conditions, the path from microbial life to technological civilization is, as the history of Earth makes clear, neither straight nor fast nor guaranteed. Life appeared on Earth somewhere between 3.5 and 3.8 billion years ago, perhaps even earlier, in the form of single-celled organisms. For the next 2 billion years, roughly half the current age of the Earth, life remained essentially single-celled. The innovation of the eukaryotic cell, the kind with a nucleus and complex internal structures, appears to have happened only once, around 2 billion years ago, through a merger between 2 distinct types of single-celled organisms. Multicellular animals did not appear until perhaps 600 to 800 million years ago. Vertebrates emerged from the sea onto land about 375 million years ago. Mammals diversified meaningfully, only after the extinction of the non-avian dinosaurs 66 million years ago. Our genus, Homo, appears in the fossil record only about 2 to 3 million years ago. Modern Homo sapiens, with our characteristic anatomy, perhaps 300,000 years ago. Agriculture and settled civilization within the last 12,000 years. Industrial technology and radio communication within the last 200. The journey from first microbial life to a species capable of radio communication took roughly 3.5 billion years, and many of the steps along that path, as paleontologist and evolutionary biologist Stephen Jay Gould argued extensively, appear to have been accidents, contingent events, evolutionary rolls of the dice that could have fallen differently. The asteroid impact 66 million years ago that ended the Cretaceous and cleared the way for mammalian expansion was not inevitable. Had it not happened, the descendants of the dinosaurs might have continued to dominate terrestrial ecosystems for another 100 million years. Intelligence might never have emerged, or it might have emerged in a completely different form, in the lineage of birds perhaps, whose cognitive abilities we have consistently underestimated. This is one of the deepest challenges in astrobiology, distinguishing between what is universal about the emergence of intelligence and what is contingent. Is intelligence, once life begins, an inevitable destination that evolution will eventually reach? Or is it a very rare and specific outcome of very particular evolutionary circumstances? The honest answer is that we don't know, and the sample size of one makes the question extremely difficult to address scientifically. Carl Sagan and Frank Drake were, in their time, champions of the view that intelligence is likely to emerge wherever complex life does, that it is sufficiently advantageous that natural selection will tend to produce it given enough time and enough ecological complexity. This view, sometimes called the principle of mediocrity or the Copernican principle, holds that Earth is not special, that the conditions here are typical, and that life and intelligence should be common outcomes of typical planetary evolution. Ward and Brownlee, and more recently researchers like David Grinspoon and others, argue the opposite, that intelligence as we know it is a specific, fragile and unlikely product of a very long and accident-prone evolutionary history, that there is no reason to expect it to appear commonly, and that the universe, for all its planetary richness, may contain very few of the cognitive miracles we take for granted when we look in the mirror. These are not fringe positions. Both are held by serious scientists at major institutions, and both make predictions about what we should expect to find as our instruments improve. If intelligence is common, SETI should eventually succeed, the James Webb Telescope should detect biosignatures on multiple worlds, and the history of the cosmos should show evidence of civilizations that expanded and built, and perhaps left detectable engineering projects visible from Earth. If intelligence is rare or unique, we will continue to hear nothing, and the silence will gradually accumulate into a kind of negative proof, never absolute, but increasingly significant with each passing decade of technological improvement and continued absence of signal. Somewhere between these two poles lies the truth we are reaching for, one careful observation at a time. There is one more dimension of this problem worth considering before we go further, a dimension that is easy to overlook but perhaps the most unsettling of all. It involves time. The universe is 13.8 billion years old. Earth is 4.6 billion years old. The first rocky planets in the Milky Way could have formed perhaps 9 or 10 billion years ago, from the heavy elements generated by the first generations of massive stars that lived fast and died violently as supernovae. Those planets had a 4 billion year head start on Earth. If life arose on any of them with anywhere near the ease it seems to have arisen here, and if intelligence followed with anywhere near the speed it has here, those civilizations would be, by now, not merely millennia ahead of us, but billions of years ahead. They would have had time to explore the entire Milky Way many times over. Even at a fraction of the speed of light, traversing the galaxy from one edge to the other takes perhaps 10 million years. Civilizations that arose 4 billion years before us could have crossed our galaxy 400 times since then. This is the temporal version of Fermi's question, and it is, if anything, more acute than the spatial version. We're not just asking where the aliens are. We're asking where the evidence of civilizations that had billions of years to expand, to build, to transform their environments has gone. Because a sufficiently advanced civilization, given enough time, should leave marks on the universe that are difficult to miss. They might dismantle entire planets to build megastructures that harvest their star's entire energy output, structures known in theoretical astrophysics as Dyson spheres, first imagined by physicist Freeman Dyson in 1960. They might alter the orbits of worlds on a scale visible from neighbouring star systems. They might broadcast signals across the entire electromagnetic spectrum with power outputs that dwarf anything produced by natural cosmic events. We see none of this. Astronomers searching for Dyson spheres and other technosignatures, the observable evidence of technology, have found no confirmed examples. The universe looks, to our best instruments, like a place shaped only by physics and chemistry and gravity, without any of the architectural signatures we might expect from a billion-year-old technological civilization. Perhaps those signatures are simply too subtle for our current instruments. Perhaps we are looking in the wrong ways or in the wrong places. Perhaps civilizations old enough to reshape galaxies do so in ways that are invisible to 21st century human technology. All of these possibilities are scientifically respectable. None of them can be ruled out. But they do not make the silence go away. They merely push it into a different register of uncertainty. What we are left with, after all of this, is a problem that is cleaner and starker than it might initially appear. The universe is vast and old and full of worlds. Life, as far as we know, requires only chemistry and energy and time, all of which the cosmos provides in staggering abundance. And yet, in all the frequencies we have listened on, in all the atmospheres we have analysed, in all the sky surveys our instruments have conducted, we have found exactly one example of a world that harbours life, the one we're standing on. That could mean the universe is mostly empty. It could mean the universe is full of life, but we simply haven't looked hard enough or in the right ways. It could mean that something prevents civilizations from persisting long enough to be detectable. It could mean that intelligence arises rarely, or that the step from intelligence to technology is not as straightforward as our own history might suggest. It could mean many things. What it cannot mean, and this is what makes the Fermi Paradox so intellectually compelling after more than 7 decades, is that the question isn't worth asking. Quite the opposite. It may be the most important question our species has ever posed, because embedded in the silence of the cosmos is not just a scientific mystery, it is a mirror. How we answer the question of why we haven't found life out there tells us something deep about what we think life is, how fragile or how robust it is, how inevitable or how accidental, how long it tends to persist once it arises. And all of those answers have implications for us, for the civilization we have built, for the one we are building, and for whether we will be around long enough to finally hear something back. Let's spend a little more time with the idea of civilizational collapse, because it occupies a central place in several competing explanations for the Fermi Paradox, and it deserves more than a passing mention. Among the most unsettling candidates for a great filter ahead of us is the possibility that technological civilization is inherently self-terminating, that the very tools which allow a species to reach the stars also carry within them the seeds of its destruction. This is not a fringe concept confined to science fiction. It has been discussed seriously by physicists, economists, and military strategists for decades. The Cold War provided the first vivid illustration. Within 15 years of developing atomic technology, humanity had accumulated enough nuclear weapons to sterilize the planet several times over. The existence of that capability, and the fact that it was not used, required a combination of decision-making restraint, institutional design, luck, and perhaps individual courage that we sometimes underestimate. Robin Hanson himself, in developing the Great Filter Framework, listed among the potential filter candidates the development of weapons of mass destruction. Not just nuclear weapons, but biological weapons engineered with precision tools that are becoming cheaper and more accessible with every passing decade, chemical weapons, and eventually, perhaps, AI systems capable of autonomous lethal action. A civilization that solves the physics problem of interstellar travel but cannot solve the political problem of managing its own destructive capacity might simply destroy itself before it has the chance to leave. Some researchers have extended this argument in a direction that feels uncomfortably near to our own present moment. The philosopher Nick Bostrom has argued that the development of artificial general intelligence, an AI system capable of improving itself recursively until it vastly surpasses human cognitive abilities, may represent a technological transition point at which a civilization either survives or doesn't. The window of risk, according to this view, is extraordinarily narrow. a species must achieve sufficient collective wisdom to manage an intelligence explosion at precisely the moment its technology makes such an explosion possible. The margin for error is very small. And if this transition is a near-universal feature of technological civilizations, then perhaps no civilization has yet managed to thread that needle successfully. If true, then the great filter lies not in the deep past of biological evolution, but in the near future of technological development, a future we are now actively entering. I want to be clear that these are hypotheses, not predictions. They are serious hypotheses, developed by serious thinkers, but they are not established science. We have no way of knowing, from our current vantage point, whether the development of powerful artificial intelligence is a catastrophic bottleneck for civilizations, or whether it is a doorway to a kind of stability and capability we cannot currently imagine. The history of technological risk is not uniformly grim. Humanity has, so far, navigated its most dangerous inventions without ending itself. Whether that navigational capacity scales as the technologies become more powerful is one of the central questions of our era. But think about what this means in cosmic terms. If civilizations regularly reach a technological threshold and then fail to survive it, the observable universe would look exactly as it does to us now. Worlds that developed life, worlds that developed intelligence, worlds that developed technology. And then, silence. Over and over again, across billions of galaxies, across billions of years, the same arc. Emergence, flourishing, destruction. No signals would escape because there was no one left to send them. No megastructures would be built because the civilizations that began them were gone before they could be completed. No colonization would take place because the ships were never launched. This is a deeply uncomfortable scenario to contemplate. It suggests that intelligence, rather than being a route to cosmic permanence, might be a kind of evolutionary cul-de-sac, a trait that provides short-term advantages but carries long-term liabilities that accumulate faster than the institutions needed to manage them. And yet there is a counter-argument. Earth has been producing radio signals that can be detected from space for roughly a century. By any cosmic standard, that is a geological eye blink. We are extraordinarily young as a technological civilization. The window during which any civilization broadcasts detectable signals before either going silent, developing superior communication technologies, or unfortunately ceasing to exist altogether, might be very narrow. If most civilizations broadcast for only a few hundred or a few thousand years before either advancing to communication methods we cannot detect or collapsing, then even a galaxy teeming with civilizations would appear quiet to an observer, listening at any random moment. The cosmic radio spectrum would be full of whispers too brief to catch, like fireflies flickering in a forest so large that the odds of seeing two of them illuminate at the same time are vanishingly small. This explanation, sometimes called the short window hypothesis, is not reassuring in the way we might hope. It does not promise us that the universe is full of thriving civilizations. It merely says that even a universe full of civilizations could look silent to us, given the timing of our emergence and the transient nature of the radio broadcasting phase of technological development. It is agnostic about whether those civilizations survived their technology or were destroyed by it. There is another hypothesis that is worth discussing here, one that takes a fundamentally different approach to the problem. Rather than asking why civilizations don't persist long enough to be detected, it asks whether civilizations that do persist might have reasons to avoid being detected. This is sometimes called the dark forest hypothesis, a term coined by Chinese science fiction author Cixin Liu in his novel of the same name, though the underlying logic predates the popular fiction. The dark forest hypothesis posits that the universe is indeed full of civilizations, some of them ancient and powerful beyond our comprehension, but that the survival logic of an advanced civilization in a universe with limited resources and unpredictable neighbours leads inevitably to one conclusion: make no noise and destroy any civilization you detect before it can threaten you. The title comes from a metaphor. Imagine a dark forest filled with armed hunters. Each hunter knows others are out there. Each hunter cannot be certain of the intentions of any other. In such a forest, the rational strategy is silence and preemptive action. Any civilization that announces itself becomes a target. The dark forest hypothesis is not a mainstream scientific proposal in the same way that the rare earth hypothesis or the great filter are. It is a philosophical argument about game theory and strategic behaviour under conditions of radical uncertainty. but it has attracted the attention of scientists and thinkers who find it, if not necessarily correct, at least not obviously absurd. Renowned astrophysicist Stephen Hawking, in his later years, expressed repeated public concern about broadcasting our existence to the cosmos, arguing that contact with a more advanced civilization could be catastrophic for humanity, drawing an analogy to what happened when technologically superior European civilizations encountered the peoples of the Americas. This concern has had practical implications. There is an ongoing debate within the SETI community about the merits of what has been called active SETI or METI, messaging extraterrestrial intelligence, the deliberate broadcasting of signals into space in hopes of contact. Some scientists argue that this is simply the reciprocal of listening, that if we want to detect others, we should also be willing to be detectable. Others, including Hawking, have argued that we should be considerably more cautious, that we have no way of knowing what kind of civilization might receive such messages or how it might choose to respond, and that the asymmetry between what we might gain from contact and what we might lose from a hostile response justifies extreme restraint. The debate remains unresolved. No formal international policy governing deliberate transmissions from Earth has been adopted, though informal norms within the scientific community have generally favoured caution. Our civilization has been inadvertently broadcasting its existence since the development of radar and television, meaning that a sphere of detectable radio signals roughly 100 light-years in radius already surrounds our solar system, expanding outward at the speed of light. Whether anyone is listening to those signals, and what they might make of them if they are, is unknown. What is clear from all of these competing frameworks is that the question of whether we are alone cannot be answered by any single instrument or any single observation. It requires a convergence of evidence from multiple directions: radio astronomy and the search for artificial signals, transmission spectroscopy of exoplanet atmospheres, the search for technosignatures in the observable universe, the study of life's origins in our own solar system, and the biological and geological reconstruction of the steps that led from chemistry to consciousness on our own world. We are building those capabilities. The James Webb Space Telescope is already returning data that was impossible to collect a decade ago. The upcoming Habitable Worlds Observatory, a proposed next-generation space telescope that NASA has identified as a priority for the 2040s, is specifically designed to search for biosignatures on Earth-like planets around Sun-like stars, a goal that Webb cannot fully achieve due to its infrared focus and the limitations of its instrument suite. The Square Kilometre Array, a radio telescope being built across sites in South Africa and Australia, will be the most sensitive radio observatory ever constructed, capable of detecting signals from exoplanets orders of magnitude fainter than anything we could previously detect. In our own solar system, the search for life is not waiting for distant instruments. NASA's Perseverance rover has been drilling cores in the ancient lakebed of Jezero crater on Mars since 2021, collecting samples that may preserve signs of ancient microbial life, if such life ever existed on the planet's surface. Those samples, secured in titanium tubes and cached in carefully marked locations on the Martian surface, are destined to be returned to Earth by a joint NASA and ESA sample return mission, though the timing and architecture of that mission remain under active discussion. The returned samples, once in terrestrial laboratories, can be subjected to the full battery of analytical chemistry that no rover could ever carry, analysis powerful enough to distinguish biogenic chemistry from purely geological processes. Europa, the icy moon of Jupiter, holds an ocean of liquid water beneath its frozen shell, kept liquid by the tidal heating generated by Jupiter's enormous gravity. That ocean, by some estimates, contains more liquid water than all of Earth's oceans combined. It has been in contact with Europa's rocky seafloor for billions of years, creating conditions that bear a striking resemblance to the deep-sea hydrothermal vent environments on Earth, where complex chemical communities, and possibly the earliest life on our planet, have been found to thrive. NASA's Europa Clipper spacecraft, launched in October 2024, is now on its way to the Jovian system, scheduled to begin its primary science mission, with close flybys of Europa starting in 2030. It will measure the depth and salinity of the subsurface ocean, search for signs of water plumes that might vent ocean material into space, and assess the moon's habitability in detail that was previously impossible. Enceladus, the small icy moon of Saturn, has already revealed something extraordinary. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew directly through plumes of water vapour, ice, and organic molecules erupting from cracks near Enceladus's south pole. Those plumes contain hydrogen molecules, silica grains that indicate hydrothermal activity, and complex organic compounds. They are, in short, a sample of what lies beneath the Moon's ice shell, delivered directly to space and available for collection. The presence of hydrogen alongside organics in a liquid water environment is precisely the chemical signature that astrobiologists look for on Earth as an indicator of environments capable of supporting life. No mission is currently approved to return to Enceladus, though proposals for a dedicated follow-up mission have been submitted to NASA and ESA. The solar system, in other words, has turned out to be far more generous with potentially habitable environments than anyone expected when Fermi asked his question in 1950. We went from believing that Earth was the only world in our solar system where life was plausible to identifying at least 4 environments where it is scientifically respectable to wonder: Mars, with its ancient lake beds and possible subsurface liquid water; Europa, with its deep ocean; Enceladus, with its active geochemistry; and even Titan, Saturn's largest moon, with its lakes of liquid methane and ethane, its thick nitrogen atmosphere, and its exotic chemistry that some researchers have speculated might support a completely different kind of life. One built not on water and carbon, but on liquid hydrocarbons and chemistry that our biology textbooks don't even cover. Every one of these environments is speculative as a habitat. None of them has yielded confirmed signs of life. But their very existence demonstrates something important: that the conditions for life, at least the liquid chemistry, energy-driven kind of life we know about, are not as rare as the early solar system appeared to suggest. They are present in multiple places around a single ordinary star. If they are present here, the logic of statistics says they are present around many other stars as well. The question of why we haven't found life, then, is not just a question about life's rarity. It is a question about the entire cascade of requirements between the presence of habitable conditions and the emergence, persistence, and detectability of intelligent civilization. Each link in that chain, from chemistry to microbes, from microbes to complex organisms, from organisms to intelligence, from intelligence to technology, from technology to communication, represents an opportunity for the process to fail or to stall. And we don't know how often each link holds. What we do know is that we're asking the question at an extraordinary moment. The instruments we now have and those we are building are the first in human history genuinely capable of finding answers. Not metaphorical answers, not philosophical arguments, but actual empirical evidence. A confirmed biosignature in an exoplanet atmosphere, a confirmed sample of ancient Martian biology, a signal from another civilization that no natural process can explain. Any one of those findings would transform our understanding of the universe more profoundly than any discovery since Copernicus moved us from the centre. And the absence of any such finding, continued across decades of increasingly sensitive searching, would itself become a discovery, perhaps the most important one of all. So we have the question, sharply defined now, stripped of its comfortable vagueness. We are not simply asking whether life exists elsewhere. We're asking why, given everything we know about the universe, the only confirmed example of life and intelligence we can point to is the one looking back at us from the mirror. And we're asking that question at the precise historical moment when our instruments have become powerful enough to begin collecting real answers, not philosophical arguments, not mathematical estimates, but actual data from actual worlds. That is an extraordinary place to be. Uncomfortable, perhaps, in the way that genuine uncertainty is always uncomfortable, but extraordinary. And it is worth taking a moment before we go further to appreciate just how rapidly the scientific landscape of this question has changed, because the speed of that change is itself part of the story. When Enrico Fermi asked his famous question in 1950, humanity had not confirmed the existence of a single planet beyond our solar system. The idea that other stars had planetary systems was widely believed, but it remained an inference rather than an observation. The technology to detect planets around other stars simply did not exist. In that context, Fermi's question was essentially a philosophical one, grounded in statistical reasoning but without the empirical foundation to make it a testable scientific hypothesis in any practical sense. By 1995, that had changed. The first confirmed exoplanet around a main sequence star had been discovered, and the door was open. By 2013, the Kepler mission had demonstrated that planets are not rare exceptions but the norm. By the early 2020s, the first detailed atmospheric spectra of exoplanets were being obtained with the James Webb Space Telescope. By 2025, a credible candidate biosignature was being seriously discussed in peer-reviewed literature. The arc from philosophical speculation to observational science has compressed into roughly 3 decades. In the span of a single human career, the question of whether other worlds exist has been answered definitively, and the question of whether those worlds harbour life has moved from the realm of science fiction into the realm of active measurement. This compression of timescales is important because it suggests that the next few decades may bring an equally dramatic acceleration in what we know. The history of discovery in astronomy is not linear. It tends to plateau for long periods and then lurch forward when new instrumentation reaches a critical threshold of capability. We appear to be approaching or entering such a threshold now, with multiple observatories coming online, multiple missions underway or in development, and the analytical power of machine learning transforming our ability to extract signal from noise in enormous datasets. What that means in practice is that the probability of a transformative discovery in the next 20 to 30 years is genuinely significant. Not certain. Science is never certain before the fact, but the conditions for a major finding are converging in a way they have never converged before. Let's take a step back and think carefully about what we mean when we say we are searching for life, because the definition matters enormously, and the confusion between different types of life leads to a great deal of muddled thinking in this field. When most people hear the phrase extraterrestrial life, they imagine something at least roughly analogous to themselves, a creature with a biology, perhaps with a nervous system, with something recognizable as behavior. But astrobiology, the scientific field dedicated to understanding the distribution and nature of life in the universe, casts a much wider net. It is interested in life in any form, from the simplest conceivable self-replicating chemistry to the most sophisticated technological civilization imaginable. And within that spectrum, the scientific community has increasingly converged on a recognition that the most likely form of life we might detect first is not the kind that would shake hands or send us a radio message. It is microbial life. Simple, single-celled, chemically versatile, potentially thriving in environments that would kill a human being in seconds. The kind of life that dominated this planet for the first 3 billion years of its existence. The kind of life that still constitutes, by biomass and by species count, the overwhelming majority of living things on Earth today. This matters because microbial life and intelligent life are, from the perspective of detectability, almost entirely different problems. Detecting intelligent life means looking for signals, for technology, for engineering on a scale visible from other star systems. Detecting microbial life means looking for atmospheric chemistry, for isotope ratios, for organic compounds arranged in configurations that chemistry alone would not produce. The tools are different, the expectations are different, and the implications are different. If we find microbial life on Europa or Mars, it tells us that the chemistry of life is not unique to Earth, that a biogenesis has happened at least twice in our own solar system. That would be one of the greatest discoveries in the history of science. But it would not tell us that intelligent life is common, and it would not resolve the Fermi Paradox. Those are separate questions, and collapsing them together leads to conclusions that the evidence does not support. The search for biosignature gases in exoplanet atmospheres is, in this sense, fundamentally a search for microbial or at least pre-technological life. The gases that would flag a living world from a distance, oxygen and ozone in chemical disequilibrium with methane, nitrous oxide, dimethyl sulfide, are primarily the products of microbial metabolism. They are the chemical exhaust of a living world in the same way that smoke from a factory chimney is the chemical exhaust of industrial activity. If the James Webb Space Telescope or its successors confirm the presence of these gases in the atmosphere of a planet in another star's habitable zone, it would be among the most profound scientific discoveries in human history. And it would still not answer Fermi's question, because microbial worlds that never give rise to intelligence would not call us, would not colonize the galaxy, would not leave the megastructures we have been watching for. Fermi was not asking where the microbes are, he was asking where everybody is. So let us hold both questions in mind simultaneously, because they are related but distinct, and the answer to one does not automatically supply the answer to the other. Life might be common, and intelligence might be rare. or both might be rare, or both might be common, and we simply have not yet looked long enough or carefully enough to find them. All three of these possibilities are scientifically respectable at this stage of the search. There is a hypothesis about the Fermi Paradox that I find particularly intellectually honest, in part because it is willing to acknowledge the possibility that we simply have not looked hard enough yet. This is sometimes called the cosmic haystack problem, and it was developed in detail by SETI researchers including Jill Tarter, the astronomer who directed the SETI Institute for decades, and whose work became one of the inspirations for Carl Sagan's novel Contact. The metaphor is simple and powerful. If you're looking for a needle in a haystack, and you search 1 cubic centimetre of that haystack and find no needle, you cannot conclude that the haystack contains no needle. You have searched an almost infinitesimally small fraction of the available space. Tarter and her colleagues have argued that the actual fraction of the electromagnetic spectrum that has been searched for artificial signals over all the frequencies, all the directions, all the timescales, and all the sensitivities of all the SETI surveys conducted to date is roughly equivalent to searching 1 glass of water drawn from the world's oceans and concluding from the absence of fish in that glass that the oceans contain no fish. We have looked, by cosmic standards, at almost nothing. The SETI search is not a decades-long comprehensive survey. It is a series of preliminary reconnaissance expeditions across a search space that is almost incomprehensibly large. And we're finding nothing in the tiny corners we have managed to examine with instruments that have only recently become adequate to the task. This is a sobering and important corrective to any temptation toward premature conclusion. The absence of a confirmed signal is not evidence of absence. It is evidence that signals of sufficient strength in the frequencies we have monitored have not yet appeared in the small fraction of parameter space we have examined. That is a very different statement, with very different implications for how we should interpret the silence, and the tools are improving with remarkable speed. The Breakthrough Listen initiative, funded with a commitment of $100 million when it launched in 2015, has brought dedicated observing time on some of the world's largest radio telescopes to the SETI search. The Greenbank Telescope in West Virginia and the Parkes Observatory in Australia have been used under Breakthrough Listen to survey tens of thousands of stars at multiple frequencies and sensitivities, far beyond anything that previous surveys achieved. The data being collected is orders of magnitude richer than anything generated before, and the analysis of that data, increasingly assisted by machine learning algorithms trained to identify subtle patterns in enormous datasets, is opening up new corners of the search space with every passing year. One of the most important recent developments in SETI research is the broadening of the search beyond radio signals. The traditional image of the SETI program, an astronomer at a console listening to cosmic static, captures only one narrow slice of the possible ways in which technological activity might manifest at interstellar distances. Researchers are now seriously investigating a far broader inventory of what are called technosignatures, observable evidence of technology rather than biology. These include laser pulses in the optical or near-infrared spectrum, which some researchers argue are actually more efficient means of interstellar communication than radio waves for civilizations with sufficiently advanced photonic technology. The Breakthrough Listen program has devoted significant resources to optical SETI searches. They include anomalous patterns of light from stars that might indicate large artificial structures orbiting them, the kind of megastructures theorized by physicist Freeman Dyson in 1960, who proposed that a sufficiently advanced civilization might eventually construct a vast sphere of collectors around its host star to capture its entire energy output. They include chemical anomalies in planetary atmospheres that go beyond biosignatures into the realm of industrial pollution, gases and compounds that could only be produced by large-scale industrial activity and that would have no plausible natural source. They include the waste heat signatures of energy-intensive civilizations, since any sufficiently advanced civilization must release heat as a thermodynamic consequence of its activity, heat that might be detectable as an anomalous infrared excess from an otherwise normal stellar system. In 2015, a peculiar star drew worldwide attention and became one of the more fascinating episodes in recent astronomical history. KIC 84628552, known informally as Tabby's star after astronomer Tabitha Boyajian, who led the study of its unusual behaviour, exhibited a pattern of light dimming that was, by any standard, genuinely puzzling. It dimmed irregularly, by amounts ranging from less than 1% to more than 20% of its total light output, at unpredictable intervals, with a profile that matched no known natural phenomenon cleanly. The initial scientific paper on the star noted that among the possible explanations, a massive artificial structure, a Dyson sphere under construction, or a collection of large orbiting megastructures, could theoretically produce such a pattern. The popular press seized on this explanation. The star made front pages around the world. For a brief heady period in 2015 and 2016, it felt as though we might be looking at the first confirmed evidence of an extraterrestrial megastructure. Multiple radio and optical SETI searches were quickly pointed at the star. No artificial signals were detected. The subsequent scientific investigation, conducted with rigour and the appropriate scepticism, has since converged on a more mundane but still scientifically interesting explanation. The dimming is most likely caused by large quantities of dust, possibly from a recent collision of cometary bodies or a fragmenting body in a distant orbit, that is periodically obscuring the star's light in complex and variable ways. The artificial structure hypothesis has not been formally and definitively ruled out, but the dust explanation accounts for the observations more parsimoniously and without requiring extraordinary assumptions. The Tabby star episode is instructive not because it turned out to be extraterrestrial engineering, but because it demonstrated that our instruments are now sensitive enough to detect anomalies that prompt this kind of systematic investigation. We are, for the first time, doing technosignature astronomy in a genuinely scientific and organised way. There is another direction in which the search for extraterrestrial life has expanded that is worth examining in some detail, and it is the study of our own solar system's past. Because if there is one thing the last several decades of planetary science have taught us, it is that conditions in our solar system were very different in the distant past than they are today, and that several environments that appear hostile now were potentially habitable for extended periods of geological time. Mars is the most obvious and compelling example. The evidence for a once habitable Mars has become overwhelming. The Curiosity rover, operating in Gale Crater since 2012, has found ancient mudstones, lacustrine sediments deposited in a lake environment, and organic chemistry suggesting that Mars hosted a stable, warm, wet environment billions of years ago. That environment persisted for timescales of millions to perhaps tens of millions of years, long enough, by the standard of Earth's own early history, for life to potentially arise. The Perseverance rover in Jezero Crater, a location chosen specifically because orbital imagery revealed features interpreted as an ancient river delta, has found further confirmation. Jezero Crater held a lake roughly 3 billion years ago. That lake was fed by rivers carrying sediment from a broader drainage basin. It deposited variegated mudstones of the kind that, on Earth, are excellent preservers of organic material and microbial biosignatures. Astrobiologists debate whether the window of habitability on Mars was long enough for life to arise. On Earth, life seems to have emerged within a few 100 million years of the planet becoming habitable, perhaps even faster. If a similar timescale applied on Mars, then a Mars that was warm and wet for tens of millions of years had, in principle, enough time. Some models suggest that Mars was continuously habitable, at least intermittently, for long enough. Others suggest that the Martian climate was more episodic, with liquid water existing in pulses driven by volcanic activity or large impacts, separated by long stretches of cold and dry and inhospitable conditions. The truth is not yet known, and it may not be known until we have the Martian rock samples in terrestrial laboratories. What is known is that if life did arise on Mars during that early wet period, it would have faced a very specific and very serious challenge as the planet changed. Mars lost its global magnetic field, apparently quite early in its history. Without a magnetic field, there was nothing to deflect the charged particle flux from the Sun, and the solar wind began to gradually erode the Martian atmosphere. Over billions of years, the atmospheric pressure dropped, the average surface temperature fell, and the liquid water that had once covered portions of the Martian surface either evaporated into the thinning atmosphere and was photodissociated and lost to space, or froze into the ground and polar caps. The surface Mars today is cold, dry, and bathed in ultraviolet and ionizing radiation at levels that would be lethal to most organisms as we know them. But the deep subsurface of Mars might tell a different story. Underground environments on Mars, shielded by meters to kilometers of rock, would be protected from radiation. Geothermal heat from the planet's interior however reduced from its early active phase, might still maintain liquid environments deep below the surface. Radar soundings from the Mars Express spacecraft have found evidence consistent with liquid water or brines beneath the Martian south polar ice cap. If liquid water exists in the Martian subsurface today, it is not unreasonable to ask whether anything living in it. This is not a mainstream claim, but it is a scientifically respectable question that current missions cannot directly answer. This brings us to one of the most important realities about the search for life in our solar system. The tools that are needed to answer the really critical questions are not the tools we currently have. The Mars rovers are extraordinary machines. They have transformed our understanding of Martian geology, geochemistry, and ancient climate. But they are not designed to definitively detect life. They are too small to carry the full suite of analytical instruments that would be needed. Their sample analysis capabilities are limited by mass and power constraints, and they cannot drill to the depths where extant life, if it exists, is most likely to be found. This is why the Mars Sample Return mission, for all the bureaucratic and financial challenges it faces, is so critical to the long-term program of Mars exploration. The samples, Perseverance has collected and cached in titanium tubes on the Martian surface, represent the best materials currently available for answering the question of Martian biology. The instruments in terrestrial laboratories that would analyze those samples can resolve isotopic ratios to parts per billion, identify organic molecules with a specificity and sensitivity no rover instrument can match, and look for the structural signatures of cellular biology in ancient rock at scales down to the nanometer. These are the tools that might actually answer the question, and they are sitting on Earth, waiting for rocks that are sitting on Mars. The Europa Clipper, now travelling toward the Jovian system on a trajectory that will take it past Mars and eventually reach Jupiter in 2030, represents a parallel investment in answering a different but equally important version of the same question. Europa's subsurface ocean is, by many estimates, the most promising environment in the solar system for finding life other than Earth itself. It is vast, it is in contact with a rocky seafloor, it is heated by tidal forces that keep it liquid despite its enormous distance from the Sun, and it has been in these conditions for billions of years. The Clipper will not land on Europa and will not directly sample its ocean. What it will do is characterize that ocean in unprecedented detail, measure its depth and salinity and chemical composition through remote sensing, map the surface features that correspond to exchange between the ocean and the ice shell, and identify the most promising targets for a future lander mission specifically designed to search for biological activity. That future lander, if it is ever built and funded and launched, would represent the next great frontier in the search for life in the solar system. A spacecraft that could melt its way through kilometers of ice, deploy into the ocean, and chemically analyze the water would be the most ambitious mission in the history of planetary science. Its cost would be enormous, and its technical challenges formidable. But the scientific return, if it found so much as a single amino acid in a configuration that could not be explained by abiotic chemistry, would dwarf any other discovery in modern science. I want to return to something I said earlier and explore it a little more carefully, because I think it is often glossed over in discussions of the Fermi Paradox, and it deserves more attention. I mentioned that the universe is extraordinarily old, and that civilizations that arose billions of years before us would have had time to expand across the galaxy many times over. This temporal argument is one of the sharpest edges of Fermi's paradox, and it has led some researchers to what might be called the simulation hypothesis or the zoo hypothesis as potential resolutions. The zoo hypothesis was proposed by astronomer John Ball in 1973. It suggests that advanced extraterrestrial civilizations are aware of us but have chosen not to make contact, treating us in the same way that a nature reserve might treat its inhabitants, observing but not interfering, allowing our development to proceed without outside influence. This could be a deliberate policy of a single civilization that has established dominance over the galaxy, or it could be an independently arrived at consensus among many civilizations, something analogous to the idea of a galactic prime directive. The appeal of this hypothesis is that it resolves the Fermi paradox without requiring either the rarity of life or the inevitability of civilizational collapse. The aliens exist, they are out there, and they are watching. The challenge with the zoo hypothesis is not that it is logically impossible. It is that it requires an implausibly perfect and universal enforcement of a policy of non-contact across all potentially communicating civilizations across billions of years of cosmic history. For the zoo to work, every civilization that achieved the capability to contact us would have had to independently choose not to, or would have had to be restrained from doing so by a coordinating authority of some kind. The history of life on Earth suggests that as complex systems become more diverse, they become harder to coordinate, not easier. 1 million independent civilizations, each with their own interests and motivations, maintaining a flawless silence toward Earth across millions of years strains credibility considerably. A related but philosophically more radical hypothesis is the simulation argument, popularized in its current form by philosopher Nick Bostrom and taken seriously enough to have been publicly endorsed by several prominent scientists and technologists. It proposes that the universe we observe might itself be a computational simulation created by a more advanced civilization or intelligence, and that the apparent absence of other intelligent life might be an artifact of that simulation's design rather than a fact about the underlying reality. If we are in a simulation, the designers of that simulation might have chosen, for reasons we cannot know, to populate it with only one example of intelligent life. The cosmic silence would then not be a fact about the universe, but a fact about the specific simulation we happen to be running inside. I raise this not because it is a mainstream scientific hypothesis, because it is not, but because it illustrates something important about the Fermi Paradox more broadly. When you push hard enough on the possible explanations for why we are alone, you eventually reach explanations that are technically unfalsifiable, that cannot be distinguished from alternative hypotheses by any observation or experiment we could currently design. This is a sign that you have reached the outer edge of what science, in its current form, can address. The cosmic silence eventually becomes a Rorschach test, shaped by the assumptions and philosophical commitments of the person staring at it. That is not a reason to stop investigating. It is a reason to be epistemically careful about conclusions and to keep pressing the empirical search rather than retreating into unfalsifiable speculation. The best response to the limits of current science is always more science, more data, more precise instruments, more carefully designed experiments. Philosophy can frame the question, but it cannot replace the observation. This is also why I want to take a moment to say directly that this is one of those topics where it is particularly valuable for you to do your own reading beyond what any single documentary or video or article can give you. The literature on the Fermi Paradox, on astrobiology, on the origin of life, and on the search for biosignatures is vast and genuinely accessible, much of it available through NASA's website, through the SETI Institute's public materials, through university repositories where preprints of scientific papers are freely available. If this documentary has sparked your curiosity, and I hope it has, there is a world of primary sources waiting for you, written by people who have devoted their careers to these questions with a rigour and depth that I can only gesture toward in the time we have here together. Let me now turn to a question that often gets overlooked in discussions of the Fermi Paradox, but which sits at its very heart. What would it actually take to recognise life if we found it? This might sound like a strange question. Surely we would know life when we see it. But the history of astrobiology, and even the history of biology on Earth, suggests that this confidence is not always warranted. When NASA's Viking landers touched down on Mars in 1976, they carried experiments specifically designed to search for signs of metabolic activity in the Martian soil. One of those experiments, the labelled release experiment designed by biologist Gilbert Levin, produced results that looked remarkably like what a biologically active soil would produce. The experiment delivered nutrient solution to a soil sample and detected the release of carbon dioxide in a pattern consistent with biological metabolism. Levin argued at the time, and has continued to argue for decades since, that his results were consistent with the presence of living organisms in the Martian soil. The scientific consensus, then and now, is that the labelled release results were more likely explained by the presence of highly reactive oxidizing chemicals in the Martian soil, which could have produced similar results through purely chemical reactions. The absence of organic molecules in the soil sample, detected by a companion experiment, further argued against a biological explanation. The Viking results remain contested in some quarters, but the mainstream scientific community does not regard them as evidence for life on Mars. The Viking episode illustrates a challenge that runs through the entire search for life. Distinguishing biology from chemistry at the frontier of detection is genuinely difficult. Life, at its most basic, is a set of chemical reactions arranged in particular ways with particular organizational structures. Recognizing the difference between chemistry that is organized by biology and chemistry that is organized by purely abiotic processes requires, in many cases, multiple independent lines of evidence converging on the same conclusion. A single anomalous measurement, however exciting, is never sufficient. The history of science, and particularly the history of astrobiology, contains too many cases where initial excitement gave way to mundane explanations when the full body of evidence was assembled. This is why the criteria developed by Sarah Seeger and others for confirming a biosignature gas detection are so valuable. They require a strong, high signal-to-noise detection. They require unambiguous identification of the specific molecule producing the spectral signal, and they require that the presence of that molecule be consistent with what is known about the planet's physical environment, ruling out abiotic mechanisms that could produce the same molecule under those conditions. These are demanding criteria. They are meant to be. The consequences of a false positive in the search for life, of announcing the discovery of extraterrestrial biology and being wrong, would be severe for the credibility of the entire field and would ultimately set back the genuine search. This caution does not make the search less exciting. It makes it more honest, and honest science is ultimately more interesting than its alternative because honest science can be trusted. There is a dimension of the life in the universe question that we have not yet addressed, and that represents one of the most active frontiers in modern chemistry and biology. It is the question of whether life as we know it, carbon-based, water-dependent, organized around the specific chemistry of DNA, RNA, and protein, is the only possible kind of life, or whether fundamentally different chemistries might produce self-replicating, metabolizing systems that we would struggle to recognize as alive at all. This question matters enormously for the Fermi Paradox because if life can take radically different chemical forms, then environments we have dismissed as uninhabitable might in fact be thriving with organisms built on entirely different principles. Saturn's moon Titan is the most often cited example. Titan has a thick nitrogen atmosphere, a surface temperature of around -179 degrees Celsius, and lakes and rivers composed of liquid methane and ethane rather than water. These conditions are incompatible with life as we understand it on Earth. But theoretical chemists have proposed that certain organic molecules could potentially form cell-like structures in liquid methane, using acetylene as an energy source in place of oxygen and photosynthesis. Such life would be extraordinarily different from anything we know, but it would not violate any known law of chemistry or physics. The search for life on Titan is, at present, largely theoretical. NASA's Dragonfly mission, a rotorcraft lander selected for development in 2019, is scheduled to arrive at Titan in the mid-2030s. It will explore the moon's surface chemistry, searching for complex organic molecules and investigating the prebiotic chemistry that is known to be active in Titan's atmosphere. It is not designed to search for living organisms directly, but the chemistry it studies may tell us whether the conditions for some form of life, however exotic, are present there. More broadly, the possibility of alternative biochemistries represents a fundamental limitation on our current search strategies. If we're only capable of recognizing life that resembles the life we already know, we might fly past an entire kingdom of alien biology without recognizing it. This is a philosophical problem as much as a practical one, and it does not have an obvious solution. It suggests that the absence of detection is even less conclusive than it might otherwise appear. Let me now consider what is perhaps the most grounding and humbling perspective on everything we have been discussing. It is a perspective that comes not from the cutting edge of astrobiology, but from the deepest history of our own planet, a history that has been decoded with increasing precision over the past several decades. Earth has been habitable for roughly 4 billion years. In that time, the biosphere has survived 5 major mass extinction events, the most severe of which, the end-Permian extinction approximately 252 million years ago, eliminated over 90% of marine species and perhaps 70% of terrestrial vertebrate species. It survived the snowball Earth episodes, periods hundreds of millions of years ago, when the planet may have been almost entirely covered in ice from pole to equator. It survived the late heavy bombardment of the early solar system, a period of intense asteroid and comet impacts that may have repeatedly sterilized the surface. And life not only survived all of this, it diversified through it, responding to each catastrophe with evolutionary experimentation that eventually produced new forms of complexity. This resilience is striking and important. Life on Earth has proven to be extraordinarily difficult to eliminate once it gets started. Even the most severe extinction events did not come close to ending the biosphere. They changed it profoundly and irreversibly. They reshaped it. But life persisted. If life is similarly resilient on other worlds, then its mere appearance, however improbable the initial step of abiogenesis, might tend to persist once it takes hold. And if it persists through the geological crises that all active planets experience, then the question of why we have not detected it becomes even more acute. The Earth's geological record also tells us something important about the relationship between life and planet. Life has not merely adapted to the Earth, it has profoundly modified the Earth. The Great Oxidation Event, which occurred approximately 2.4 billion years ago, was caused by cyanobacteria pumping oxygen into an atmosphere that had previously been essentially free of it. That event transformed the planet's chemistry, eventually making possible the oxygen-rich atmosphere in which complex animals could evolve. The entire carbonate-silicate cycle, the planetary thermostat we discussed earlier, is deeply intertwined with biological activity. Life and planet co-evolve, shaping each other over geological time in ways that no abiotic chemistry alone could produce. This co-evolution is why researchers looking for biosignatures focus on chemical disequilibrium in planetary atmospheres. A living world leaves its mark not just in specific molecules, but in the overall chemical state of its atmosphere, a state that departs from the thermodynamic equilibrium that chemistry alone would produce. Earth's atmosphere, with its simultaneous abundance of oxygen, methane, and nitrogen, is deeply out of thermodynamic equilibrium. Maintaining that disequilibrium requires constant biological input. Without life, the oxygen and methane would react with each other and disappear on timescales of thousands of years. Their simultaneous presence, at the levels observed, is a direct fingerprint of biology operating at planetary scale. This is the kind of signal the next generation of space telescopes will be designed to detect. Now, I want to spend some time with the emotional and philosophical landscape of this question, not because feelings are evidence, but because the way we hold this question affects how seriously we pursue it, how we interpret the answers, and ultimately what we do with those answers. The possibility that we are alone, truly alone, in a universe of 100 sextillion planets is one of the most vertiginous thoughts available to a human mind. It asks us to contemplate a cosmos that has been burning for 13.8 billion years, that has produced galaxy upon galaxy, star upon star, world upon world, all of it evolving and changing and complexifying over timescales that no human lifetime can meaningfully traverse, and to sit with the possibility that in all of that, consciousness emerged exactly once, here, on this small blue world, around this unremarkable middle-aged star in this quiet corner of the Milky Way. Some people find this thought desolating. It strips the cosmos of the company that makes it bearable. Others find it clarifying, even elevating. If we are the universe's only witnesses, if consciousness arose here and nowhere else, then everything we do and everything we preserve and everything we understand matters in an absolute sense. The responsibility it places on us is extraordinary. The extinction of our civilization, in this scenario, would not just be a tragedy for humanity. It would be a final silence in a cosmos that has been building toward awareness for almost 14 billion years. Carl Sagan, who spent his career arguing that life was likely to be common in the cosmos, also held on to something important regardless of which direction the answer pointed. He wrote with characteristic clarity that we are made of star stuff. The atoms in our bodies were forged in the nuclear furnaces of ancient stars that exploded before the sun was born, scattering their elements across the galaxy. Those elements coalesced into the sun, into the planets, and eventually into us. In this sense, the universe has always been becoming conscious. The question is only whether it did so here alone or in many places simultaneously. Either answer is extraordinary. Either answer demands that we take the question seriously. And either answer is one that our generation, for the first time in human history, has the tools to begin addressing empirically rather than philosophically. This is what makes the present moment so singular. We are the first humans who can point a telescope at a planet orbiting another star and detect the gases in its atmosphere. We are the first humans who can drill into the ancient rock of another planet and collect samples for analysis. We are the first humans who can listen, systematically and with real sensitivity, to the electromagnetic spectrum of the galaxy and ask whether any of what we hear is artificial. We are, in the most literal sense, the generation that first became capable of finding out. What we will find, we cannot know. The universe has never made promises. It has never arranged itself to satisfy our expectations or spare our feelings. The data will be what the data is, and when it arrives, whether it is the bleak beauty of confirmed solitude or the staggering revelation of a second genesis, it will change everything we thought we knew about our place in the order of things. 75 years have passed since Enrico Fermi blurted his question over a cafeteria table in New Mexico. The physicists at that table laughed because the question landed with such obvious force that no one needed it explained. They understood what he was getting at immediately. They had no answer then. They would have no answer for most of the century that followed. We are still working on it, and now, for the first time, we are working on it with instruments that might actually be adequate to the task. The silence continues, for now. But the listening is finally beginning in earnest, and in the history of science, that has always been the moment when the world was about to change. Let us look more carefully at some of the specific candidates for what a great filter might actually be, because the theoretical frameworks around this concept have become considerably more sophisticated in recent years. The original formulation by Robin Hanson listed several possible filters, and researchers since have refined and extended that list in ways that draw on our expanding knowledge of planetary science, evolutionary biology, and the history of technological civilization on Earth. One of the most biologically compelling candidates for a filter behind us is the transition from prokaryotic to eukaryotic life. This transition, which occurred roughly 2 billion years ago, was not a gradual evolutionary step, but something closer to a biological merger. The eukaryotic cell, the kind of cell that makes up every plant, every animal, every fungus, and every protozoan that has ever existed, contains within it a structure called the mitochondrion, which generates most of the cell's energy. Mitochondria are not original parts of the eukaryotic cell. They were once independent bacteria, absorbed by a larger cell and, rather than being digested, retained in a symbiotic relationship that persists to this day. Every mitochondrion in every cell in your body retains its own small circular genome, a direct inheritance from that ancient bacterial ancestor. This event, called the endosymbiotic origin of the mitochondrion, appears from the genetic evidence to have happened exactly once in the history of life on Earth. Not twice, not dozens of times, once. Every eukaryotic organism alive today, and every eukaryotic organism that has ever lived, traces its ancestry back to that single, improbable merger event. If it had not happened, or if the merged cell had not survived, Earth today might still be a world populated exclusively by bacteria and archaea, single-celled organisms without nuclei, without sexual reproduction, without the capacity for the kind of genetic combinatorial complexity that makes complex multicellular life possible. Evolutionary biologist Nick Lane has argued in considerable technical detail that the endosymbiotic origin of the mitochondrion was the pivotal improbable step in the history of life on Earth. The energy per gene available to eukaryotic cells, by virtue of their mitochondria, is thousands of times greater than the energy per gene available to prokaryotic cells. This energetic jump is what made it possible for cells to evolve larger genomes, more complex regulatory networks, and ultimately the multicellular organization that produced animals. Without that energetic revolution, the constraints of prokaryotic metabolism might have kept life small and simple indefinitely. If Lane is right, then the great filter behind us may not be a biogenesis itself, which might be relatively common wherever the right chemistry is present, but the endosymbiotic event that gave rise to the eukaryotic cell, which may be extraordinarily rare. A universe of bacteria thriving on planet after planet, none of them ever managing the improbable bacterial merger that kicks off the machinery of complexity, would look from the outside exactly like an empty universe. The bacteria would not broadcast. They would not build telescopes. They would not ask questions about whether anyone else was out there. They would just metabolize, quietly and invisibly, for billions of years, invisible to any civilization trying to detect technosignatures or biosignature gases. This possibility is deeply interesting precisely because it is testable, at least in principle. If we discover microbial life on Mars, or in the ocean of Europa, or elsewhere in the solar system, the next critical question would be whether that life is prokaryotic or eukaryotic, whether it has made the leap to cellular complexity, or whether it remains confined to the simple single-celled world of bacteria and archaea. Prokaryotic life found independently elsewhere in the solar system would support the view that abiogenesis is not the filter, but would leave open the question of whether the eukaryotic transition is. Eukaryotic life found elsewhere would push the filter further along still. Another candidate for a filter behind us involves the emergence of sexual reproduction. Asexual organisms reproduce by copying themselves, passing their genes intact to their offspring. Sexual organisms combine the genetic material of two parents, shuffling and recombining genes in every generation. This combinatorial process is dramatically more powerful as an evolutionary engine than asexual reproduction, because it generates far more genetic diversity far more rapidly, giving natural selection a much richer set of variations to work with. The evolution of complex multicellular life, with its vast diversity of cell types and tissues and organs, appears to depend on sexual reproduction as the mechanism generating the variation on which selection acts. But sexual reproduction requires, at minimum, two different mating types, a coordination problem that is not trivially solved. The evolution of sex carries costs as well as benefits. Males, in sexually reproducing species, do not directly produce offspring themselves. They consume resources that could otherwise go toward reproduction. The twofold cost of males, as evolutionary theorists have called it, means that asexual reproduction has a significant short-term fitness advantage over sexual reproduction in many environments. Understanding why sex evolved and why it has been maintained in the overwhelming majority of complex life forms, despite its costs, remains one of the classic puzzles of evolutionary biology. If the evolution of sex is itself improbable, another near-singular event in the history of life that could have easily not happened, then it joins abiogenesis and the eukaryotic transition as a candidate great filter behind us, one of the many improbable steps that had to be navigated for our kind of intelligence to eventually emerge. The cumulative picture painted by these biological considerations is sobering, not because it rules out life elsewhere, but because it suggests that even granting the easy emergence of microbial life, the subsequent path to intelligence is laced with bottlenecks, each of which might be extraordinarily difficult to pass. The great filter, on this view, might not be a single catastrophic barrier, but a long gauntlet of improbable transitions, each one possible but unlikely, with the probability of threading all of them, reducing the expected number of intelligent civilizations in the observable universe to something very small. This interpretation, sometimes called the rare steps hypothesis, was developed in detail by paleontologists and evolutionary biologists who note that the major transitions in the history of life on Earth each seem to have happened very few times, often only once. The evolution of photosynthesis, the great oxidation event, the eukaryotic cell, the emergence of multicellularity, which appears to have evolved independently perhaps 24 times in different lineages, but has only produced complex animal-like multicellularity once. The Cambrian explosion, the transition from sea to land, the origin of flight, which evolved independently at least 4 times among vertebrates, suggesting it may be more evolutionarily accessible than some of the other transitions. Each time we see a major innovation arising independently multiple times, it suggests that innovation is under positive selective pressure and relatively easy to reach through evolution, given the right ecological conditions. Each time we see a major innovation arising only once, it suggests something else, either that the innovation is extraordinarily unlikely to occur by chance, or that it occurred once, and then its descendant lineages so thoroughly occupied the ecological space that no subsequent independent origination could gain a foothold. In some cases, we cannot distinguish between these two explanations from the biological record alone. The endosymbiotic origin of the mitochondrion happened once, but we cannot know whether that was because the event is extraordinarily improbable, or because once it happened, the resulting eukaryotes were so much more energetically capable that they displaced or consumed any other cells that might have been on the same evolutionary trajectory. Science often operates in exactly this kind of ambiguity, where the observation constrains but does not determine the interpretation. What is clear from all of this is that the question of why we haven't found life, on its deepest level, is really a question about the structure of evolutionary possibility, about how many paths through the combinatorial space of chemistry and biology actually lead to intelligence, and how narrow or wide those paths are. We have walked one of those paths to its terminus, we are the result. And from where we stand, we cannot yet see whether the path we walked was a broad highway that most life-bearing worlds eventually find, or a nearly invisible trail through a vast and trackless wilderness that we stumbled upon by a combination of chance and circumstance that may never be repeated. What we can do, and what we are doing, with the tools available to us, is look for footprints, signs that something else has been here, or is here, or has passed through. Not the impressions of boots in mud, but the chemical signatures of metabolisms at work, the electromagnetic whisper of technology at radio frequencies, the spectral fingerprints of biosignature gases in the light filtered through alien air. These are the footprints we know how to look for. There may be others we have not yet thought to search for, prints left by forms of life or intelligence that we have not imagined. This is why the Fermi Paradox is not just a problem about extraterrestrial life. It is a problem about the limits of our own imagination. We search for signals in the frequencies we use. We look for biosignatures produced by the chemistry we know. We imagine civilizations that develop along trajectories that mirror our own. All of our search strategies are, in some sense, projections of what we are on to what might be out there. And the universe, as every generation of scientists discovers, has a persistent habit of being stranger than anyone anticipated. The history of astronomy is replete with examples. Pulsars were discovered by a graduate student named Jocelyn Bell Burnell, who noticed an anomalous and perfectly regular signal in her radio data that her supervisor initially nicknamed LGM, for Little Green Men, because it was so artificially precise that an artificial origin seemed possible. It turned out to be a rapidly rotating neutron star, a class of object that had been theorized but whose electromagnetic behavior had not been predicted in detail. The signal was not artificial. But the story illustrates exactly the kind of encounter with the genuinely unexpected that astronomical observation regularly produces. Quasars, when first discovered, were so energetically anomalous that serious scientists proposed exotic explanations before settling on the now well-established understanding of them as the active cause of distant galaxies, powered by supermassive black holes consuming material at tremendous rates. Fast radio bursts, intense millisecond pulses of electromagnetic radiation from extragalactic distances are still not fully explained, though natural explanations involving extremely magnetized neutron stars called magnetars have gained significant support. The universe keeps producing phenomena that were not predicted and must be puzzled out from the data. In that context, the possibility that an anomalous signal, an unusual star, a surprising atmospheric composition on a distant world, or an unexpected chemical abundance in a planetary sample might turn out to be evidence of life is not a fantasy. It is a scientifically reasonable expectation that the universe, in its vast and varied complexity, will eventually hand us something that demands that interpretation. The question is whether we are looking carefully enough and in enough different ways to recognize it when it arrives. And so we return to the central reality that defines this entire enterprise. We are searching. We have been searching in earnest for less than a century, with instruments of real sensitivity for a far shorter period. We are searching a cosmos that is 13.8 billion years old and 93 billion light-years across, with tools that are, in cosmic terms, brand new. The search is young, the universe is ancient, and the silence, for all its weight and all its implication, has not yet told us its final word. Frank Drake, who started all of this in practical terms with his radio telescope pointed at Tau Ceti and Epsilon Eridani in 1960, once said that we might be expected to find evidence of extraterrestrial intelligence within the next 20 years of serious searching. He said that at various points in his career, and the 20 years kept moving forward without the discovery arriving. But Drake also said something else that has stayed with me since I first encountered it. He said that the discovery, when it comes, will change everything, not just science. Not just cosmology, everything. The way we think about ourselves, about our obligations to each other and to the future, about what it means to be alive and conscious in a universe where those qualities are either precious or commonplace. He was right about that. Regardless of when the discovery comes, or whether it comes in the form of a confirmed signal or a biosignature, or a Martian fossil or something we have not yet thought to look for, when it arrives, it will be the answer to the question that has sat at the back of every human mind that ever looked up at the night sky and wondered, quietly, whether the lights up there meant anything to anyone else. We do not know the answer yet, But we are, for the first time, asking the question with instruments that are up to the task. That is not a small thing. In the history of our species, it may turn out to be the most consequential scientific program ever undertaken. Whatever we find, we will be ready to understand it. That is what science does, and this question, the oldest and deepest and strangest question our species has ever asked, deserves nothing less than our very best. There is one final perspective I want to share before we close, and it concerns the relationship between the search for life and the project of understanding ourselves. Because in a very real sense, these are the same project. Every question we ask about the origin and prevalence of life in the universe is also a question about how we came to exist. Every candidate great filter we identify and examine tells us something about how improbable or how robust the chain of events was that produced us. Every biosignature we look for in an exoplanet atmosphere is a proxy for the chemistry that, on this planet, became alive. Every Mars sample we collect is a potential mirror held up to the ancient Earth, showing us what our own world looked like before life transformed it. In this sense, the search for extraterrestrial life is not separate from the project of understanding life on Earth. They are the same investigation approach from two different directions. From one direction, we study the molecular mechanisms and evolutionary history of life on Earth, tracing the thread from the RNA world back toward the first self-replicating chemistry, and forward from there through every transition that led to us. From the other direction, we look outward at the universe and ask how often those same conditions and those same transitions occur elsewhere. When those two investigations eventually meet, when the understanding of how life arose here connects with the data about where life exists out there, we will have something approaching a genuine theory of life in the universe. Not a philosophical speculation or a mathematical estimate, but an empirically grounded understanding of how common or how rare consciousness is in the cosmos. That understanding, when it arrives, will be one of the great achievements of the scientific enterprise, worth placing alongside the theory of evolution, the discovery of DNA, and the development of quantum mechanics as a fundamental reorganization of how we understand reality. We are not there yet. The data is incomplete. The questions outnumber the answers by an enormous margin. The silence of the universe has not yet been broken, or if it has, we haven't heard it. But the questions are being asked with tools that are finally adequate to the task, and the answers, in whatever form they take, are now within the reach of human science. That is where we are. Right here, at this particular moment, with these particular instruments, on this particular world. Looking up, and for the first time in the long history of our species, genuinely capable of hearing an answer. This has been Deep Space Intelligence. I'm Liam. The search continues, and I'm grateful you're following it alongside us. Until next time, keep looking up, keep questioning what you hear, and never stop asking. Before I go, I want to pause and say something that has been on my mind throughout the making of this documentary. We have covered an enormous amount of ground today, from the physics of exoplanet detection to the chemistry of the RNA world to the evolutionary bottlenecks that might stand between microbial life and technological intelligence. And if there is one meta-lesson that all of this science offers, it is that the history of ideas about life in the universe is a history of surprises. Almost every confident expectation has been revised. Planets turned out to be ubiquitous when they were expected to be rare. Mars turned out to have had lakes and rivers when it was expected to be geologically dead. Complex organics turned out to be present throughout interstellar space when life's building blocks were expected to be confined to the thin habitable surfaces of a few lucky worlds. The universe has a consistent track record of exceeding our prior expectations, and also of withholding the specific confirmation we most want, not out of cruelty, but out of indifference to what we want. That should make us humble about the silence, not resigned, not defeated, but genuinely humble. Because if the history of science tells us anything, it is that absence of detection is not absence of reality. X-rays were real before we knew they existed. Black holes were real before we had the instruments to confirm them. The Higgs boson was real before the Large Hadron Collider found it. The universe does not wait for our permission or our instruments to contain what it contains. Life, if it exists beyond Earth, is real regardless of whether we have yet found it. If it does not exist, the universe's emptiness is real, regardless of how strange and unsettling that emptiness feels to us. Our task, as always in science, is simply to find out. With patience, with rigour, with instruments that improve every year, and with the intellectual honesty to follow the data wherever it leads, even if it leads somewhere we did not expect and did not want to go. The question Fermi asked over lunch in 1950 has survived every generation of inquiry without a definitive answer, and that survival is itself a testament to the depth and difficulty of what it is asking. It is not a question that will yield to a single experiment or a single observation or a single moment of revelation. It will yield slowly, through the accumulation of evidence from many directions, over many years, interpreted by many minds. That is how the hardest scientific questions are eventually answered. We are part of that process, all of us who watch and read and think about these things, who fund and encourage and pay attention to the science, who keep the question alive in the culture as well as in the laboratory. The search for life in the universe belongs to all of humanity, not just to the scientists who conduct it, and the answer, when it comes, will belong to all of us too. Thank you for spending this time thinking through it alongside me. This has been Deep Space Intelligence, and I am Liam. We will see you in the next episode. And one last thing, a reminder I try to give at some point in every documentary we make here, because I think it genuinely matters. Everything you have heard in this episode represents our best current understanding of the science, drawn from peer-reviewed research and the work of some of the most careful and dedicated scientists in the world. But science is not a body of final truth. It is a process of ongoing revision in response to new evidence, and the field of astrobiology in particular is moving faster right now than almost any other area of science. What is a tentative hypothesis today may be confirmed or refuted by next year's data. What is considered settled may be overturned by an unexpected observation. The papers, the primary literature, the actual scientific publications where these findings are reported and debated are freely accessible to anyone who wants to go deeper. I would encourage you to do exactly that, not to take my word or anyone else's as the final verdict on any of this, but to engage with the science directly, follow the citations, read the papers, and form your own understanding. That is the spirit in which this channel exists, not to deliver conclusions, but to accompany you in the inquiry. That is the spirit, I believe, in which the best science is done, and it is the spirit in which the universe's deepest questions deserve to be explored. The cosmos has been silent for as long as we have been listening. But listening itself is an act of faith, a bet that the universe has something to say, that the information is out there encoded in light and radio waves and molecular spectra, waiting for instruments sensitive enough and minds open enough to receive it. Every generation that has looked up at the night sky and wondered has been part of that act of listening, even the generations that had no instruments at all, only their eyes and their imaginations and the questions that human minds cannot seem to stop asking. We are the generation that gets to listen with real ears. That is an honour that does not require any particular answer to justify it. The listening, pursued honestly and patiently, and without predetermined conclusions, is its own reward. And somewhere out there, across the incomprehensible scale of the universe we have inherited, the answer to Fermi's question is waiting to be found.